Section. Introduction. In the field of artificial intelligence, there's a long-standing goal to create versatile assistants that can follow users' instructions across various tasks, especially those involving multiple modes of input. Recently, there's been a surge of interest in developing foundational models that can understand and generate responses in a variety of tasks, using different types of input. Large language models, LLMs, like ChatGPT have proven effective in creating general-purpose assistants for tasks involving natural language. However, the challenge of creating similar assistants for tasks involving computer vision and vision language tasks is still being explored. Current efforts in developing these multimodal agents can be divided into two main approaches. The first approach involves end-to-end training with LLMs. Here, data from image text and multimodal instruction following tasks are collected and used to train LLMs to process visual information. This results in large multimodal models, LMMs, that have shown impressive visual understanding and reasoning capabilities. Examples of these models include Flamingo, Multimodal GPT-4, LLaVA, and MiniGPT-4. Despite their effectiveness, it's still a challenge to develop a unified architecture that can incorporate a wide range of skills, such as image segmentation and generation, which are crucial for real-world multimodal applications. The second approach involves tool chaining with LLMs. In this method, prompts are carefully designed to enable LLMs to use different tools, such as pre-trained vision models, to perform desired tasks without additional model training. Examples of this approach include VisProg, Viper GPT, Visual Chat GPT, XGPT, and ImReact. The strength of this method is its ability to perform a wide range of visual tasks using new tools, which can be incorporated into an AI agent at a low development cost. However, this method is not adaptable or robust enough to always accurately select and activate the appropriate tools and combine their results to generate final answers for real-world multimodal tasks. In this paper, we introduce LLaVA+, a general-purpose multimodal assistant that learns to use tools using an end-to-end training approach. This approach systematically expands the capabilities of LMMs through visual instruction tuning. To our knowledge, this is the first attempt to combine the strengths of the end-to-end training and tool chaining methods. LLaVA+ is equipped with a skill repository that contains a wide range of vision and vision language tools. The design is based on the society of mind concept, where each tool is designed for a specific skill and is only useful for specific scenarios. However, when these tools are combined, they lead to emergent abilities that show signs of higher intelligence. LLaVA+ can construct a new workflow on the fly, given users multimodal inputs, select and activate relevant tools from the skill repository, and combine their execution results to fulfill many real-world tasks that were not seen during model training. LLaVA+ can be continually improved by incorporating new skills or tools through instruction tuning. For example, if a new multimodal tool has been developed for a specific scenario or skill, we collect relevant user instructions that request this tool and their execution results to form instruction following data for tuning. After instruction tuning, LLaVA+ expands its abilities as it learns to use this new tool to deal with tasks that it could not handle before. Unlike existing works on teaching LLMs to use tools, where visual signals are only used when the multimodal tools are activated, LLaVA+ uses the raw visual signals throughout the entire human-AI interaction sessions to improve LMM's ability of planning and reasoning. In summary, our paper makes the following contributions. 1. We present a new pipeline for curating vision-language instruction following data, dedicated for tool use in human-AI interaction sessions, leveraging ChatGPT and GPT-4 as labeling tools. 2. We have developed LLaVA+, a general-purpose multimodal assistant that extends LLaVA by incorporating a large and diverse set of external tools that can be selected, composed, and activated on the fly for performing tasks. Our empirical study validates the effectiveness of LLaVA+ with consistently improved results on multiple benchmarks, and in particular, new SOTA on VisitBench with a diverse set of real-life tasks. 3. We will release the following assets to the public: the generated multimodal instruction data, the codebase, the LLaVA+ checkpoints, and a visual chat demo. Section Summary. The paper introduces LLaVA+, a general-purpose multimodal assistant that combines end-to-end training and tool chaining methods. LLaVA+ learns to use a wide range of vision and vision language tools through instruction tuning, allowing it to construct workflows on the fly and perform various real-world tasks. The empirical study demonstrates the effectiveness of LLaVA+, achieving state-of-the-art results on multiple benchmarks and offering open-source assets for further exploration. Section: Learning to use tools with visual instruction tuning. Our work is inspired by the remarkable performance of multimodal GPT-4 and open-source language image multimodal models, LMMs, like LLaVA-GPT-4. We've seen a rise in the development of LMMs and multimodal instruction following the instruction tuning paradigm. In this paper, we use LLaVA as an example, but our proposed method can be easily applied to other LMMs. LMMs like LLaVA typically start with a user-provided image query. They then accept a natural language instruction from the user and output a natural language response. We can represent multimodal instruction following data using a unified scheme. This scheme includes special role tokens for the human and assistant, a line break token, and a sequence end token. This scheme can cover any multimodal tasks that involve language image input and language output. These tasks can range from simple visual understanding tasks like recognition, captioning, and visual question answering to complex visual reasoning tasks. The data pipeline is simple and easy to construct and scale. By training a single transformer-based model with an auto-regressive objective, the resulting LMM enables a seamless human-assistant interaction, proficiently completing many visual tasks. However, it has limitations in terms of skill expansion and engagement in human-AI interactions. To address these limitations, we propose a modularized system architecture called LLaVA+. This system allows an LMM to learn to use a wide range of skills at scale, facilitating easy expansion of its capabilities and interface. We build a skill repository where the LMM can leverage a broad range of existing vision and vision language specialist models as tools for their respective skills when needed. Unlike most existing multimodal agents, LLaVA+ performs skill-oriented dialogues. Here, the LMM initiates requests to call appropriate tools from the skill repository and subsequently aggregates the tool execution results after applying the proper skills. LLaVA+ works in 4 steps. 1. Humans provide a task instruction related to an image. 2. The LMM-powered assistant analyzes both the instruction and the image, and outputs a command that chooses the tool from the skill repository and writes the appropriate prompt as the tool argument. 3. By executing the tool, the result is returned to the assistant. 4. The assistant aggregates the result with the instruction and the image, and outputs an answer to humans. Compared with the training of LLaVA, the only new component for LLaVA+ training is the skill-oriented dialogue. LLaVA+ uses a unified model prediction format to represent dialogues with and without the need of calling the skill repository. This format consists of 3 fields. 1. Thought. A text sequence representing a reasoning process, which determines whether the skill repository is needed to follow the user instruction, and if so, which tools to use. 2. Action. A list of function calls for the tools to execute the thought. The list is in the JSON format, with each item consisting of 2 subfields, API_name to call the tool and API_params for the corresponding function arguments if applicable. When action is an empty list, no skill is invoked. 3. Value. A natural language response that LLaVA+ generates by aggregating tool execution results and the human-AI session history. In the serving stage, we find it important to ensure a good user experience that we only return the content in the value field of the answer to human users, but hide the entire skill-oriented dialogues unless we need to debug the system. Section Summary. The paper introduces LLaVA+, a modularized system architecture that allows a language and vision model, LMM, to learn and use a wide range of skills. This enables the LMM to expand its capabilities and interface, and perform both user-oriented and skill-oriented dialogues, resulting in a more flexible and engaging human-AI interaction. The LLaVA+ model uses a unified prediction format to represent dialogues, which includes a thought sequence, action list for tool execution, and a value field for generating natural language responses. Section. Skill Repository. Multimodal tool use instruct data generation. In our project, we've created a repository of various skills for a system we call LLaVA+. This system uses a variety of tools to complete tasks, and it needs specific instruction data to know which tool to use at any given time. We've used a method called self-instruction to gather this data, with the help of a language model called GPT-4. Our goal is to equip LLaVA-Plus with new skills that the original LLaVA system doesn't have. These include individual skills for understanding and generating visuals, retrieving external knowledge, and combining these skills. We've categorized these skills into two groups: core skills, which are essential, and extended skills, which enhance the system's capabilities. Core skills are all about understanding visuals. Current language models can only understand a limited range of visuals, but we've expanded this to include a wider variety of visual inputs and outputs. These include detecting and grounding objects, segmenting images semantically or by instance, tagging, captioning, and optical character recognition, OCR, among others. We've divided these skills into two types: those that only need an image, and those that need additional function arguments. For skills that only need an image, we've created training samples for each tool. We've used GPT-4 to generate instructions that require the use of tools for proper answers. We've also used it to generate thoughts and values for the skill use and answer, and to generate responses to form instruction following data. For skills that need additional function arguments, like object detection and instance segmentation, we've used two methods. The first is similar to the image-only skill setting, but with a placeholder concept that gets replaced with one or more categories from the image. The second method involves using GPT-4 to generate questions based on two seed samples and image contexts. Our extended skills enhance the capabilities of LLaVA+. We've onboarded a variety of multimodal tools to demonstrate the system's versatility. We've also enabled the system to retrieve external knowledge, generate and edit images, follow visual prompts, and combine skills to handle real-world tasks. For example, we've curated data for scenarios where various visual understanding results of the same image are required in a multi-turn human-AI interaction session. We've also enabled inpainting with visual interaction by combining segmentation results from user pointing and a tool called Stable Diffusion, SD. We've enabled instructional visual condition generation by combining the spatial layout from OpenSeed semantic segmentation and ControlNet. And we've made it easier for users to generate social media posts that contain both images and text by using SD to generate an image, or instruct Pix2Pix to edit an image, then combining the image with its description generated by a pre-trained language model. Section Summary. The skill repository of LLaVA+ consists of multimodal tools with different skills, and to ensure the most appropriate tools are activated, the corresponding tool use multimodal instruction following data is curated using the self-instruct method with GPT-4 as the labeler. The study focuses on enabling LLaVA+ to handle scenarios that require novel skills, such as visual understanding, generation, and external knowledge retrieval, and the instruction data is curated by filling in data variables using different strategies. Section. Model Training and Serving. We're going to discuss how we trained and implemented LLaVA+, a model that combines tool use instruction data with the LLaVA 158K dataset. To make this work, we had to convert the LLaVA 158K dataset into a unified prediction format. We did this by treating the responses in the dataset as values and adding fields of thoughts and actions using templates. We built LLaVA+ in two different ways. The first way, which we call LLaVA+, All Tools, uses tool use as external knowledge. We used all visual understanding tools, except for segmentation, to process the input image. The results were then organized into symbolic sequence representations to enhance the image features during both training and evaluation stages. The second way, LLaVA+, Fly, uses tools on the fly to reduce the cost of using all tools. We only provided the execution results of related tools for a given instruction. When we report our results, we trained models on the 81K understanding instruction data because existing benchmarks mainly focus on understanding capabilities. However, when we built demo systems, we trained our models on the full dataset. We served LLaVA+ using the fast chat system, which includes web servers that interact with humans, model workers that host the LMM and multiple tools, and a controller to coordinate the web server and model workers. The 7B LLaVA+ and all the tools can be loaded and served in an 80G GPU. We also compared LLaVA-Plus with existing general-purpose multimodal systems. These systems can be broadly categorized into two classes. The first class includes AI agents that use multiple tools with LLMs to solve complex, open-world problems. The second class includes unified models with versatile multimodal capabilities. LLaVA-Plus is the first work that uses the LMM as the planner for tool use, where image inputs are considered throughout the entire interaction sessions for improved user experience. Compared to other models, LLaVA-Plus enables a much wider range of multimodal skills and their compositions. We evaluated LLaVA-Plus using two benchmarks. The first benchmark, LLaVA Bench, evaluates the visual chat of LMMs with three types of questions: conversation, detailed description, and visual reasoning. The second benchmark, SEED Bench, evaluates the image level and instance level perception and reasoning of LMMs with 19K multi-choice questions. Both LLaVA-Plus variants outperformed LLaVA on these two benchmarks, demonstrating the effectiveness of adding visual recognition results of applying new skills in the LMM pipeline. LLaVA-Plus, all tools, performed better than LLaVA-Plus, Fly, because it uses more tools as additional contexts. We also conducted several tests to further understand the performance of LLaVA-Plus. We found that directly adding the skill execution results in the testing stage of LLaVA resulted in lower performance, indicating the importance of learning to use skills and training. We also found that removing thoughts in the unified data format resulted in a performance drop, indicating the benefit of a chain of thoughts style data format. Finally, we found that visual instruction tuning of tool use in LLaVA-Plus is important, as indicated by the lower performance of GPT-4 tools, which trains an LLM for multimodal tool use. Section Summary. LLaVA-Plus is trained by combining curated tool use instruction data with the LLaVA 158K dataset, and it is built in two settings: LLaVA-Plus, all tools, and LLaVA-Plus, Fly. LLaVA-Plus is served using the fast chat system, and it outperforms LLaVA on benchmarks for visual chat and perception and reasoning tasks. Section. LLaVA Bench, Tools. We've developed a new evaluation set, LLaVA Bench, Tools, to assess the innovative abilities that come with learning to use skills. This set measures four capabilities: grounding, tagging, captioning, and OCR, optical character recognition, with a varying number of samples for each. We've compared our system, LLaVA-Plus, with commercial visual chat systems like Microsoft's Bing Chat and Google's Bard. Our system significantly outperforms these others on this benchmark, primarily because they lack some of these capabilities. We've also compared our system with GPT-4 and ImReact, demonstrating the benefits of training an open-source language model multimodal, LMM, as a planner for tool use. Another comparison was made with the state-of-the-art LMM systems. MMVet, which contains 200 images and 218 questions, was used to evaluate 6 core vision language capabilities and their combinations. An LLM-based evaluator was used to score open-ended outputs of different forms. LLaVA-Plus consistently outperforms LLaVA on both 7B and 13B model sizes, with the most significant improvements seen in OCR and spatial categories. This indicates the positive impact of the corresponding visual skills on LMM outputs. VisitBench, a real-world use-oriented LMM benchmark, was also used. It comprises 592 questions and 1,159 public images categorized into 70 instruction families. The results were evaluated using a system similar to a chess rating system, where each pairwise human judgment is treated as a match. The difference between the ratings of two models provides an estimate for the win probability when one model is pitted against another. LLaVA-Plus significantly outperforms the leading method LLaVA by over 100 points, setting a new standard on the leaderboard. We've also illustrated new capabilities of LLaVA-Plus with visual examples. For instance, in one example, the system successfully detects the coordinates of a frisbee, helping to determine its status of flying in the air and thus describe the outdoor scene, activity. In another example, we demonstrate an interactive image editing scenario, where users aim to see the spatial layout of the scene first and then generate an image of a similar layout, but with a new, underwater, scene. LLaVA-Plus not only applies the correct skills, but also generates a function argument for conditional image generation. In another example, we show that LLaVA-Plus can be used to help create multimodal social media posts. For instance, when capturing an image, the user wants to post the same image in an autumn scene and associate the image with some attractive text to post on Instagram. LLaVA-Plus can use the editing skills to revise the image and combine the context of visual images and their related language topics to suggest several caption options. We've created all 4 seasons for the same scenarios and observed that LLaVA-Plus can follow the instruction to easily switch among them while consistently maintaining the original image queue.